Today we are going to discuss proof by contradiction, which is one of the most powerful types of proof in mathematics. It is powerful because it can be used to prove any statement in several fields of mathematics. The structure is remarkably simple. Assume the statement to be proven is false, and work to show its falsity until the result of that assumption is a contradiction. Suppose you want to believe in the truth of a mathematical statement like this one. No integers y and z exist for which 24y plus 12z equals 1. With proof by contradiction, you set out to prove the statement is false. This is often easier than proving it to be true. You continue along with your proof until you run into something that does not make sense. This is when you showed that the statement must be true since you cannot prove it to be false. Let's break it down into the steps we follow when using proof by contradiction. Assume your statement to be false. Proceed as you would with a direct proof. Come across a contradiction. State that because of the contradiction, it cannot be the case that the statement is false, so it must be true. Truth and falsity are opposites. If one exists, then the other cannot. This is a basic rule of logic, and proof by contradiction depends upon it. Truth and falsity are mutually exclusive, so that a statement cannot be true and false at the same time. If the statement can be proven true, then it cannot be false. If the statement can be proven false, then it cannot be true. If the statement cannot be proven true, then it is false. If the statement cannot be proven false, then it is true. It is that last condition of truth and falsity that is exploited, powerfully and universally, by proof by contradiction. Let's look at the same example from earlier. No integers y and z exist for which 24y plus 12z equals 1. You could spend days, weeks, years stumbling around with specific numbers to show that every integer you try works in the statement. Using proof by contradiction, though, we could try to prove the statement false. No integers y and z exist for which 24y plus 12z equals 1. To prove this false, we take the position that we can find integers y and z to make the equation work out. Start with the original equation. 24y plus 12z equals 1. Divide both sides by 12, the greatest common factor. 2y plus z equals 1 divided by 12. Immediately we are struck by dividing both sides by the greatest common factor of the two integers. The sum of the integers is a fraction. That is a contradiction. Two integers cannot add together to yield a non-integer, aka a fraction. This contradiction means the statement cannot be proven false. It must therefore be true. Perhaps the most famous example of proof by contradiction is this. The square root of 2 is irrational. Our proof will attempt to show that this is false. We will attempt to show that the square root of 2 is rational. A rational number can be written as a ratio or a fraction. Any fraction can be simplified to its irreducible form. So 2 by 6 we can simplify to 1 by 3, but can be simplified no further. Notice in its simplified form at least one term of the fraction is odd. An irrational number cannot be expressed as a fraction or a ratio. Numbers like pi and Euler's number are irrational, having no fractional equivalent. So we are saying that the square root of 2 is some irreducible fraction a by b, such that a or b is odd, or both a and b are odd. Square root of 2 equals a divided by b. So we square both sides to get 2 equals a squared divided by b squared. Then we multiply both sides by b squared to get 2b squared equals a squared. Here we can see that a squared has to be an even number, because the square of every even number is even, and the square of every odd number is odd. Recall that a and b cannot both be even, so b must be odd. If a is an even number, Some number exists for a equals 2c, and we can replace a with 2c everywhere we had a in our equation. 2b squared equals 2c squared. 2b squared equals 4c squared. b squared equals 2c squared. The contradiction emerges. B squared is even, so b is even. But we just got through showing it was odd. It is also contradicted because if a is even and b is even, the fraction is not in simplest form. But we started by saying it was irreducible. The square root of 2 cannot be rational, so it must be irrational. You have proven the truth of a statement by showing that a claim that is false cannot hold up to logic.